All right, hello everyone. My name is Vinny. This is Deesh, Stu, Charlie, and Austin, and our project is AutoScan, and our customer is Professor Kia. AutoScan is an automated vehicle-mounted pothole detection system tailored for use by municipalities. It's comprised of a scanning bar for pothole detection and volumetric analysis and an accompanying pothole management website, which allows the user to easily interact with pothole data on an embedded Google map. The goal of our project is to provide a systematic way for municipalities to find, detect, and repair potholes in a timely manner. Here's a photo of the finalized AutoScan case with its top propped open. In a normal daily use, the top will be latch closed and the entire system will be mounted underneath the bumper of a city bus. Inside, the downward-facing camera allows us to perform pothole detection and volumetric analysis, and a GPRS unit allows us to send this data offline, off the scanning bar to our accompanying website and management system pictured here. You can clearly see that the embedded Google map allows the user easy access to pothole data. Stu will elaborate on the website a little bit later. I'll introduce Austin to give a brief technical overview of the project.
So the AutoScan system has 6 main technical components, the first of which is the Gizmo development board. It is a single board computer that uses an accelerated processing unit from AMD to provide us with all necessary computing and image processing power that we need. We're also running a lightweight operating system called Light Ubuntu 12.07. Our next module is the DepthSense 325 time-of-flight camera. This provides us with a way to have running depth information of the road surface for pothole detection and volumetric analysis. Our next 2 modules are the Telite GM862 as well as the GE864 quad modules. These modules allow us to obtain GPS coordinates of the potholes as well as transmit pothole information packets to an offsite database through the cellular network. We also have a custom printed circuit board, which houses a power conversion unit, as well as a breakout circuit for the GM862 module, and a battery status LED circuit, which is routed to the outside of the case. We also have a power system on board through the means of a lithium-ion battery. We also have an onboard charger for utilization by the user. We're also using the Apache HTTP and MySQL database servers to host our AutoScan website. My main role in this project has been a systems integration lead. The first interface that we've used is interfacing the camera with the development board itself. That has been done by implementing various Linux drivers through a USB 2.0 connection. We've also had to integrate the GPS and cellular data modules through a USB to UART chip from FTDI, and that's mounted on the development board as well. We also have had to integrate power. We've integrated that via multiple wire harnesses and through the power conversion unit. I was also responsible for kind of tackling the environmental challenge with our product, as the underside of a bus is not a very friendly environment. So our case itself is weatherproof. It has a gasket-enclosed top cover as well as a water-resistant venting system. It's also made out of impact-resistant plastic that is able to, for anticipated collision with road debris. The system itself is also very user-friendly, as it is entirely standalone, and all the user has to do is, at the push of a button, turn it on. That powers the system, which boots up the Gizmo board, and then that starts pothole data transmission to the website. And here is Deesh to give us more information on the power systems.
So I was in charge of powering the system, and in order to do this, we implemented a rechargeable lithium-ion battery, which makes the system stand alone. That way we don't have to rely on vehicle power. We also implemented a custom printed circuit board, which has 3 parts to it. The first is a battery level indicator, which uses 2 LEDs to signify the battery level. The second is a voltage regulator, which regulates voltage from the battery to power the GM862. And lastly, we have a breakout circuit for the GM862 to map out all its pins. And we also have an onboard charging unit within the system to make it easier for the user, so that when they remove the system from under the vehicle, they can just plug it into the nearest wall socket. Now Vinny's going to tell us about image processing.
So my role on the project was to develop the image processing algorithm for pothole detection and volumetric analysis. This was done by using the DepthSense 325 time-of-flight camera from SoftKinetic. Now this is a really unique part of our project, because instead of choosing to use a regular color camera, we decided to use a time-of-flight camera. And what this does is it detects the phase difference of reflected light, infrared light, from objects within its field of view, and with this information, it can detect depth information. Our algorithm uses this information to construct a running average of the road height underneath the scanning bar as it goes across the surface. We then identify areas that are significantly lower than the road height as potholes, and then use the camera fan-out angles to determine the pothole's volume. This information is then sent off to Charlie Scripts, which appends GPS data and then uses the cellular module to send it off to the website. He'll expand on this process a little bit more.
So the image processing tells us when there is a pothole and how big that pothole is. And now what the AutoScan system needs to do is figure out where that pothole is within a municipality so it can be repaired. And then it also needs to be able to send all the potholes information to be displayed on the website. As the networking and GPS lead, I developed a Python script that completes these tasks. The script runs as a background process on the development board, and upon pothole detection, it obtains the current coordinates of the system and then encapsulates all the information about the pothole, that being the volume of the pothole, the latitude, the longitude, and also the date and time of detection, and uses a cellularly enabled TCP IP connection to send it to the remote server to be displayed on the website. My script had to interface with two pieces of hardware to accomplish this. The first being the Telit GM862, which is the GPS module, and the second being a Telit GE864, which is a GSM cellular module, which allows for data transmission to the website that Stu's going to talk about now.
Hello, my name is Stuart, and in my role as the software lead for AutoScan, I built from the ground up the AutoScan Pothole Management System website. The backend is primarily implemented in PHP, and the front end and UI are implemented using JavaScript, jQuery, and the open source library Bootstrap. The two sides communicate using asynchronous JavaScript requests in JSON format. The main feature of the website is shown here, an embedded Google map that uses map markers to display the location of potholes that our scanning bar detects. The information about the potholes, such as latitude, longitude, volume, and date of detection, is also displayed in tabular format in the bottom left. I also implemented a scheduling system that allows city municipalities to schedule repair jobs for potholes, making it easier to track who is going to repair these potholes and when. The potholes that have pending repair jobs have yellow markers indicating that they're waiting to be fixed, whereas detected potholes that are not yet scheduled for repair are indicated in red. In addition, our system is very easy to use by the user because clicking a marker centers on its location and displays additional data. Clicking a row in either table also centers on the pothole, so it's very easy to find specific potholes that you're using. You can also sort these tables by any metric on the column, so if you wanted to find the largest pothole or the most recently detected pothole, you can do that easily. To schedule a repair, a system administrator merely needs to click a button, and this drop-down page appears. The information such as pothole ID, the person assigning the job, and the date that the job is assigned on is dynamically generated by PHP and used to populate those static fields. So then a system administrator merely needs to select a worker using the pull-down list, and clicking the repair date field creates this pop-up calendar. Clicking a date or typing in the date allows the system administrator to select a date for the repair job. Then that means that a repair job is created for that pothole, and a certain user is responsible for repairing that pothole on that date. Now we're going to show you a quick video of our full system functionality. I'm trying. So normally our system would be mounted on the underside of a bus, but we don't own a bus, so we had to do this manually. We also did higher speed testing with a car, but we got similar results. So the scanning bar moved over the pothole, and now that you log into the website, you'll see that a marker was automatically created in the correct location. Let's create a repair job for this pothole. So we click a button, select a user, select a date that we want the repair job to be scheduled for, and click the Schedule Repair button. The marker turns yellow, indicating that a repair job is pending for that pothole. So let's say we fixed it, we're great city workers, it's already fixed, complete the job, and the marker is removed from the map, indicating that the pothole no longer exists. However, records are still kept on a history page so that municipalities can keep track of previously repaired potholes in locations. This also helps them identify metrics such as problem areas within the city where you have recurring potholes. AutoScan solves a unique and relevant real-world problem that affects millions of users every day. It's also possible to expand our design to larger scales of implementation by putting multiple scanning bars on multiple city vehicles at the same time. Then you have simultaneous pothole detection occurring around the city, and the data is all stored in the same easy-to-use web interface. We would like to extend special thank yous to Professors Kia and Persano for the tremendous amount of help that they've given us this semester, as well as to all the guys over at EPIC who have helped us fabricate the case. Thank you.
pothole management system, it wasn't part of the initial specifications?
So initially, one of the engineering requirements was to design a system that would display the potholes just using Google Maps, and then we kind of took it from there and elaborated on the scheduling system.
The other question is there a way, because some potholes we can describe to the road, and some potholes can be the size of a car, bus. Is there a way to prioritize potholes or to display based on the way you figure?
So you can sort the tables on the website. So if you wanted to look for the larger potholes, you can sort the tables both up and down by volume. So you would sort for the top for volume, and you could see the largest potholes that are detected regardless of location.
The system is binary, right? It's either say it's there or not. No way to basically detect it to how dangerous it is.
Well, you're talking about the image processing? Well, the image processing actually performs a volumetric analysis. It determines the spatial resolution of each pixel that it can see, and then it can determine the volume of the pothole itself. So we do have an idea of the size of each one that's detected.
Professor Conrad.
ES325 is a TOF camera with fused laser light. It doesn't work outdoors.
It does work outdoors. We've tested it outdoors before.
Not according to manufacturers, only indoor use. And if you flood with the sunlight, if enough of IR, it will basically flood your scene. So did you test it outdoors?
Yes, it's recommended for indoor use, but we've tested it outdoors at high speed, and we've had accurate detection.
With sunlight?
Yes.
Yes.
And also, we are going to implement a lens shielding, which is actually only infrared transmittive. It's a type of plexiglass, type of acrylite itself. That's entirely opaque to UV, to visible light as well.
It's also planned to be mounted underneath the vehicle, which would be slightly darker than regular conditions.
I'm sorry?
Well, since we use a time-of-flight camera, we're using depth instead of color for image processing. Anything that's raised above will not be detected as a pothole. Since we create an average of the road surface over multiple frames, well, anything that's depressed below the road would only be detected as a pothole. Nothing that's raised above it.
So that you get similar results for actually attaching it to the cars and everything. Can you expand on what you mean by similar? Like, is there a range of speeds you guys think this will work for, and does that accuracy give the pothole size and things like that? I think that's going to be effective.
So our requirement for high-speed detection was for accurate detection of up to speeds of 30 miles per hour, which we tested up to, and we were able to achieve accuracy of 30 centimeters cubed. That's 30 milliliters, so that's pretty small. Also, in terms of pothole detection, when a city crew is dispatched to go repair potholes, they usually send a crew with a truck full of asphalt. They're not going to go out with a specific amount of asphalt to fill one pothole. So the more important information is the GPS, although the volumetric data is accurate.
And naturally, too, you have better detection at slower speeds, but the 30 milliliter accuracy was at 30 miles an hour. Yeah.
Where is your website live? Is that like something you have on the device, or is that something you have like in a cloud service?
Yeah, so it's currently being hosted on our lab computer downstairs and implemented manually, though if you were to sell this as a product, you would probably use an external hosting service.
And then I guess my second question is around like your data model, or how you're doing security. I imagine that municipalities would not just want this open. Like, how do you tackle that? How do you secure that?
So all the data is protected using an open source PHP library. It creates secure sessions for PHP that don't let you actually manipulate the data unless you're logged in. As for the transmission between the scanning bar and the website, that's something that we have thought of, but due to time constraints, we weren't able to implement. We would probably use a public key style encryption and sign our own root certificates, and then install certificates on the scanning bars so that they could access our socket.
Were you able to develop an algorithm to determine where potholes are, if you're in a tunnel or if you use GPS?
The way we dealt with that is, for GPS, you can't really avoid the problem if you're in a tunnel. You're not going to get a GPS signal. So what we do is we detect it, record it in a buffer, and as soon as we get GPS or in cellular reception, we send it with a special flag denoting that it was detected at this time, and that at the time of detection, there was not GPS signal.
So you guys in the video, like ran the thing right over the pothole. What's the actual width that it can view over?
So when it's elevated at 1.5 feet, which is our estimate for being mounted underneath the bus, but due to the camera fan-out angles, the field of view is 4 feet wide and 6 feet long.
This system does not work in inclement weather, but it is waterproof and weatherproof.
Thank you.